Hello. In today's lecture, we will discuss about the ripple factor of the inductor filter that we studied in the last lecture. And then we will see how to calculate the ripple factors because it is the most important quantity for any filter circuit. The ripple factor, as I have told you many times in the last lectures, that it is the ratio of the AC to the DC components. You can say ripple factor is the remnant AC or the remaining AC in the DC output after rectification. So we have seen what is the capacitor filter. The capacitor filter reduces the AC to some AC components ripple factors to some extent. There are other filters also. The next one is inductor filter, and in this inductor filter we will see how the ripple factor is calculated. We saw about the inductor filter, we studied about the inductor filter and its working in the last section. The basic principle is that an inductor opposes any change in current. This is the working principle. Working principle of inductor filter is that the inductor opposes change in current, opposes any change in current. This is the working principle. Here in the diagram you can see a full wave rectifier and the inductor connected in series with the load. So it is called series inductor filter. Series inductor filter, because RL load resistance and L are in series. So you can see in the next diagram, these diagrams you can get in any textbook of electronics like B.K. Mehta and Thareja and Amos Smith, Boylsted and your Ryder. So without filtering this is the output, and with filtering this is the output. Now we will see how to calculate the ripple factor. So as we have seen, ripple factor, it is the component of AC that is present in the output DC. The inductor presents high impedance to the AC components. This is the working principle. I told you in the next lecture, you can see in the suggestion video or in the playlist, that the inductive reactance, it is omega times L. So high frequency components are blocked. High frequency components are blocked by the inductor. Blocked by the inductor. This is the basic principle. Capacitance stops the low frequency components and this opposes the high frequency components. So it provides a high impedance to the AC components in the output, and their amplitude is reduced with respect to the DC component. So ripples are reduced. So inductor L produces high impedance. High impedance. Impedance means blockage or stoppage. Impede means to slow down. Let me tell you the meaning. Impede means to slow down. Slow the process. Impedance to the AC components that are present in the output. AC components in the output. So the ripple factor is reduced. Ripple factor is reduced. This is the basic working of the inductor. Now let us calculate the ripple factor of this L filter or inductor filter or choke. I told you in the last video why it is called choke. So let us come to our point. So in order to calculate the ripple factor, what we have to do, we have to find the DC component and then we have to find the AC component, then we have to take the ratio between the two. So in the last previous lectures, when I discussed about the ripple factor calculation, I told you that the output voltage is expanded in Fourier series. After expanding the output voltage in Fourier series, what we get is Vi, and you have to expand it in the Fourier series, so it is the peak voltage. Then you have in the Fourier expansion 2 by pi, and there are high frequency terms, so we will take the only next high frequency term. Other harmonics we will neglect for the timing. 4 by 3 cos 2 omega t, and then you have some terms containing 3 omega t, 4 omega t, and so on. We will neglect these terms and we will consider the second harmonic only. We will consider the second harmonic only. The second harmonic is the term that contains the factor omega, harmonic only. So we are considering this 4 by 3 pi cos 2 omega t term only, and higher terms are neglected because the inductor will oppose the high frequency terms, so we can neglect the higher frequency terms because they will be automatically stopped by the inductor. Now this is the output voltage. To find the ripple factor, we have to calculate the DC component, that DC component of voltage that occurs over the load resistance. For the time being, we are considering that the choke coil or the inductor coil has no resistance, but it may have some resistance. We will see what is the correction factor for that. And the entire DC component is available at the across the load resistance, and its value will be VDC. VDC is 2 times VIP by pi. VIP by pi. Here we have considered that the resistance of the choke coil or the inductor, resistance of the choke or inductor is negligible, and the voltage drop occurs across RL only. So we are taking this assumption. If there is a voltage drop across the inductor also, we will see what will be the correction. So we are considering the second harmonic only, that is the 4 VIP cos 2 omega t by 3 pi. This is the component that we are considering. It has frequency 2 omega. Higher harmonic voltage is 3 omega, 4 omega will be neglected. So this second harmonic voltage, this second harmonic voltage partially drops over the inductor and partially over the RL. This is the significant feature of the second harmonic voltage, this cos 2 omega factor. The second harmonic voltage 4 by 3 VIP cos 2 omega t drops partially across RL and XL. This is the significant feature. Now the choke coil and the load resistance, they are connected in series. So what will be the maximum voltage drop over RL? The maximum voltage drop over RL will be 4 VIP. Maximum voltage drop, this will be 4 VIP by 3 pi into XC, sorry, it is RL and then you have in the denominator a very important term which is called the impedance, RL square plus XL square. This is called impedance. If you have studied in the chapter of alternating currents, you must be familiar with this term. This is called impedance. Now we have to calculate for AC, we need the RMS voltage drop across RL. Vrms across RL will give the AC component, This will give the AC component. So how we will get the AC component? It is 4 VIP by 3 root 2 pi, and then you have RL by R, the impedance term. You can write it in a short form also, but I am writing in the details for clarity. This is the AC component. So you have got the DC here and you have got the AC here, and now you can calculate the gamma, the ripple factor, by taking the ratio between the two, VAC by VDC. VAC by VDC gives the ripple factor, and putting the two values that you have got here, what you get after simplification? You get a factor something like this. Root over 2 will remain, pi will cancel out, and then you have this quantity 1 plus RL square by XL square. This is the quantity that you are getting. So if you put the second harmonic, if XL is 2 omega L, if XL is 2 omega L, you can put this 2 omega L here, and this, then what you will get? You will get a quantity something like this. Let me write the equation. You will get a quantity something like this, root over 2, then 3, then 1 plus 4 omega square L square by RL square. 4 omega square L square by RL square. Now you can simplify it, and in the simplified process, you have to take an assumption that this quantity 4 omega square L square, it is much less than 4 omega square L square by RL square, it is much greater than 1. If this quantity is much greater than 1, in this approximation RL square is much greater than 1, what you get? Gamma, the ripple factor is RL by 3 root 2 omega L. Sorry, it is RL by 3 root 2 omega L. Now this is the expression for your ripple factor for choke filter. Now in this expression, what you notice is that gamma will be large if load resistance is large. Gamma will be less, ripple factor will be less if load resistance is less or the load current increases. This is the important factor. So gamma will be less. We are concerned about the less gamma situation, less ripple factor situation. So we will discuss this. Gamma will be less if RL is less. RL is less means there is load current that is increasing. There is a greater load current. And the next thing what you observe here, this is omega L, this is inductive reactance. So if the inductive reactance is large, means it can suppress more changes in current or more ripples. So omega L, greater omega L reduces gamma. Gamma will be less for large XL, which is omega L, inductive reactance. So this is about your inductive filter. So here you can see the difference between the capacitive and inductive filter is that in the case of capacitive shunt filter, if RL decreases, ripple factor increases. You can see the last video. And here is the difference. Difference from, let me write it here in short form, C filter. This is the difference from C filter. If someone asks you what is the difference between the ripple factor of the inductive filter and what is the difference between the ripple factor of the inductive and the capacitor filter, you can answer this question. That in capacitor filter, if RL is less, gamma will be large. But in inductive filter, if RL is less, gamma will be less. So this is about your capacitive filter, inductive filter. Now we come to the next situation. Here you can see the diagram. This is a LC filter. LC filter. Now why this LC filter is used? We have seen two kinds of filters. Sometimes in some textbooks it is written choke input filter or LC filter. You can call it LC filter. Why it is used? We have seen two situations. Inductor and capacitance both reduce the, what you call it, your ripple factor. So this is a combination of L and C, and here you can see that L and C are both energy storing devices. L and C, inductor and capacitor, are both energy storing devices. Energy storing devices. And the next thing that you should take in consideration is that XL is omega L and XC is 1 by omega C. So the response or the reactance of inductance and capacitance to frequency is opposite. This increases with frequency, this decreases with frequency. One opposes AC, one opposes DC. So they have opposite behavior. And this is the factor that is used. So rather than individually using L or C, this combination has been observed to reduce the ripple much better, or it can produce much better filtering with RL, with a load resistance. Inductor filter, we have seen in the last section that inductor filter, what it is doing, it is decreasing with RL, but the capacitor filter, it increases with RL. So the combination of L and C makes the ripple factor independent of RL, as gamma for L filter decreases as RL decreases, but gamma for C filter increases as RL decreases. So a combination of L and C makes the gamma independent of RL. If someone asks you what is the advantage of using a combination of L and C, LC circuit is a very important circuit. When you are studying this AC, so if someone asks you that what is the advantage of using this combination of L and C, you can answer the question. You can say that this combination makes the ripple factor independent of the load resistance. As in capacitor filter, if you increase the load resistance, gamma will decrease. But in the L filter, if you increase the load resistance, gamma will increase. There is direct proportionality in L, inverse proportionality in C. But this combination makes the gamma independent of your load resistance. Or in many times, a question is asked so that gamma for LC filter is independent of load resistance. So you can show it. How you can show it? You can show it like this. If we consider the ripple factor, how to find ripple factor of LC circuit. LC circuit. If we can neglect for the time being the resistance of the choke resistance, then the DC voltage that is available across the inductor, across the load RL, as we have seen in the last section, it is 2 VIP by pi. 2 VIP by pi. This is the load, this across the load, this is the voltage. The AC drop over the RL, the load resistance, is same across the capacitor. And if we consider that the capacitive reactance is much less than RL, then we have a parallel combination of load resistance and capacitive reactance whose impedance is approximately XC. Now here also we will consider the second harmonic voltage that is occurring, that is assumed to be dropped over the LC series combination, because effectively in the overall circuit RL is not there. RL is not there. Let me show you the diagram here again. We are considering all these situations for a full wave rectifier because its rectification is better compared to the half wave rectifier. This is the condition. So equivalently you have a combination of C and combination of XC and RL in a parallel arrangement. If we consider the choke resistance and capacitor resistance are small than RL, then what we can consider? We can consider a parallel combination of XC and RL, and of course we are taking this assumption that XC is much less than RL. So here also we will consider the second harmonic voltage as we considered in the last section. So the second harmonic voltage is, this is causing the ripple. Second harmonic, I have a habit of writing the things in detail, so it may take some time. Have some patience. Second harmonic voltage or component you can write causes ripples. So we are again considering this 4 VIP by 3 cos 2 omega t. This is the second harmonic voltage, and this voltage drop occurs across the LC, as we are considering that this second harmonic voltage is occurring across this LC as RL is not there. This second harmonic is occurring across LC. So what we have, the maximum voltage drop that is occurring over the capacitor, the maximum voltage drop across the capacitor is voltage across capacitor. It is 4 VIP by 3 pi, and this is XC, XL plus XC. For cos 2 omega t, we are considering the situation when 2 omega t is maximum value. This is the situation. Now, to find the gamma, the ripple factor, we have to find the AC value. Again, we will use the same procedure. We will find the AC component by taking the RMS value, and this is again comes out to be 3 root 2 pi VIP into XC by XL plus XC. This is the RMS value. Now gamma is VAC by VDC. So what we have? This 4 VIP by 3 root 2 pi into XL by XL plus XC. And don't confuse here that we should write the DC value as this one, because many of the students are confused. The DC value is again the average value, that is 2 by pi, 2 VIP by pi. So VIP will go in the numerator and it will be 2 here, again VIP. So this will be cancelled. Pi will be in the numerator also. Pi is cancelled. This comes out to be root 2 XC by 3 XL under the assumption that XC is much less than XL. So this is the condition. So the current, DC current that is flowing through the capacitor, through the circuit is IDC is 2 VIP by pi RL. This is the maximum value, and now we have to find the maximum value of the second harmonic. This is the maximum, this is under the maximum value of second harmonic. Cos 2 omega t. 2 omega t is 1. This is the maximum value. Now the critical value of choke inductance, for this circuit, critical choke inductance for this circuit is L is RL by 3 omega L. This is the critical value of choke inductance. So here you can see that this is the, you can see the advantage, and you can see how to calculate the ripple factor of a LC filter. The next filter that we will consider, this is the RC filter. This is very familiar to you, because RC circuit, it is taught in the electrical circuits and fundamental part. RC circuit or RC filter, this is also a kind of filter. Whenever you are connecting any energy storing device, any inertia element like capacitor or inductor, you have a filtering process. So this is the RC filter, and the diagram is shown here. This is connected again to a full wave rectifier that is providing a voltage VIP. Now the DC component that is dropping over RL is, you have two resistances here. One is the load resistance, another is the connected resistance. VDC across load resistance RL is 2 VIP by pi, and the combination of R and RL. 2 VIP by pi, and it is RL by R plus RL. Now for finding the ripple factor, what you have to do, you have to find the AC component. It is again 1 upon root 2 4 VIP. We are considering the second harmonic here also, and then when you are considering the frequency dependent terms, you have to take the impedance, and it is RS square plus XC square. Remember, when you are considering the AC, the wave-like term, you have to consider the second harmonic voltage. And here also our capacitive reactance, it is much less than RL. So we are using this assumption. So VAC comes out to be this component, or you can simplify it as 4 VIP by 3 root 2 pi XC by root over 1 plus XC square by RS square. Now you can calculate the gamma by taking the ratio of VAC by VDC, and it comes out to be 1 plus R by 2. You can simplify it. Because of time constraint, I am writing the result. omega CR. Now notice this, this is the time constant. This is the time constant. So if you have a larger time constant CR, then gamma will be reduced. Gamma will be reduced. The physics behind this mathematics is that the larger time constant, the more time the capacitor takes to discharge between the peaks, as I have told you in the last section. So this is another kind of filter. And the last type of filter is the pi filter. This one is the CLC or pi filter. This is called pi CLC or pi filter, because if you are connecting the C, L and C, it appears as pi, so it is called pi filter. This circuit, this filter, it gives much better filtering than LC filter circuit. C1 is connected across the supply, and it needs a high pulse of current to charge if the load current is large. So there are some problems with high current pulses that can damage the rectifier diode. This rectifier has a restriction that it is used in a low current situation or in a low current equipment or a circuit. This filter requires high current pulse, as C1 is connected to supply, so it is used in low current equipment to avoid damage, because very high current surge or pulse, it can damage the rectifier equipment. To avoid damage, this is the fundamental thing about this pi filter. This filter gives somewhat high output voltage and its voltage regulation, but the voltage regulation, it is not as good as the LC filter. Now the ripple factor, I am writing here the result directly because the derivation is not asked generally. It is after calculation 5700 by LC1C2RL. LC1C2RL. This is the gamma. So its voltage regulation is not very good, but it reduces the ripple to maximum extent. Now in this, this is the final of your rectifiers. One important component that I should discuss with you, because it is in most of the cases it is not discussed. It is called a bleeder resistor. Bleed means if something is bleeding, if blood is coming out, if you are injured, blood is coming out, it is called bleeding. So this is called bleeder resistor. Now this rectifier circuit has in many cases this bleeder resistor RB that is placed across the filter output. It has some functions. What are the functions? You must know. First is it improves the voltage regulation of the supply. So it is connected just before the load. There is a voltage drop across RB or the bleeder resistors. There is a voltage drop here. Okay. So what does this voltage drop do? When the real load is connected, there is then only a small amount of additional drop. So the no load and the maximum load difference is reduced, and this is called voltage regulation. Improves voltage regulation. Voltage regulation, as it causes a voltage drop before load. Voltage drop before load. So no load and maximum load voltage drop difference is reduced, and that is called voltage regulation. Now why it is called bleeder? It is called bleeder because when the power supply is switched off, the capacitors discharged through this resistance. So when you are accidentally, suppose you are touching this circuit when the power is switched off, but capacitor stores charge, and you must have seen that capacitor causes sparks. So in that case you will be protected from any shock, because the capacitor will discharge through RB and it will protect you from any shock. Let me try to give you a diagram. So this is the basic requirement, and this is why it is called bleeder resistance. Let me first give you a diagram so that you can understand it better. This is kind of spark that occurs when you are using a capacitor and you are connecting its two terminals with a wire, and this can be very dangerous. So what happens when the power is switched off, when the power is switched off, then the capacitors discharge through bleeder resistor or RB. That is why it is called bleeding. It is called bleeding. Gradually the blood is coming out, or the flow is coming out through this resistor, and it saves the user from shock. Because many times it happens, there is no power supply and we are very careless, you are touching the ends of the capacitor, it can cause a high shock. So during the power supply off mode, the capacitor discharges through this resistor or bleeds through this resistor, and you are saved, you are protected from any unwanted accident. So this is the content that I had to discuss today. In the next section we will start the transistor. Although I have given some lectures on transistor, preliminary lectures, you can see them. We will see what is the transistor and how the amplification works on, and my teaching method you have seen that I try to explain in detail, so it may take some time. Have some patience, watch the videos, and please like and subscribe and share. Thank you.